My name is Mihail, and I'm a researcher from University of Coimbra. And today I want to show you some of the tools that we have developed for the PeneloPe project. It was one of the initiatives that we had here at the University of Coimbra. So the topic was zero programming tools, and we tried to find to develop a tool or to develop a solution using different tools in order to transfer manufacturing skills from humans to robots. So, and to make this transition in a very easy way that it will not require for you highly specialized technicians. Um, yes, the proposition and motivation for this work, especially on the PeneloPe project, we had one of the pilot lines that was focused on gluing of it's adhesive applications. It was gluing like big windows for the bus and coach industry. And one of their goals was to try to take those skills of their technicians. So they have specialized technicians that to put the glue on the windows, and usually it was a manual process for them, the gluing of the windows, and they wanted to automatize this process. So the idea was to take these technicians, to take the skills of these technicians and transfer it to the robot, to a robotic system. So for that, we had a solution here at the University of Coimbra that we wanted to propose, that is to use a magnetic tracker in order to get the trajectories, more or less, the trajectories and the trajectory and the orientation of the tools used by the different technicians, and by taking that data, trying to transfer it in a more seamless way to the robot. So this Polymus Liberty magnetic tracker is it has a 6 degree of freedom tracking, so it can provide to you in real time data like position and orientation. So it can give you X, Y, Z in terms of Cartesian coordinates, and in terms of the orientation, it has an output as yaw, pitch, and roll. This magnetic tracker, it's an electromagnetic sensor, so it uses magnetic fields uh, in order to determine the position in space of its sensor. So as you can see in this image, usually it has a source. So this is like this zero position, okay, is the base, and then it has a sensor. And the output of uh, this tool will be the Cartesian coordinates plus orientation of this magnetic sensor in relation to this base, okay? So in terms of precision, this usually have very high precision, but in controlled environments. Also, since it has it's a magnetic tracker. It has influences in precision if it has some magnetic fields beside him, and also metallic parts also could influence the output. So if we want to have precise data, precise output data, we should use usually um, to try to avoid environments that have that have metals or some magnetic fields, so to avoid interference. And in our case, we wanted to apply this in robotics. So we use it to capture the human manufacturing skills. Uh, Basically, we put this sensor, as you see here, we attach it to the tool that a technician would be using, being it a gluing gun um, or a torch, for example, for welding, because we have tried this also for welding. So in that case, we would be able to track, to see uh, the orientation and also the position of that tool in space. So that will be the way that the technician will hold that that tool. And since we have the position and orientation of that tool, we've usually quite good precision. Later on, I will tell you that we have some problems in terms of accuracy, but we find a way to make it quite precise. So, in terms of orientation, we achieved some results around turning around one around 2 degrees of error. And regarding the position, we had some problems with that because sometimes we could have like a few centimeters of error, not too many centimeters, but a few centimeters of error, which in this precise type of applications is not acceptable. So we tried to merge this, to make sensor merge more or less, and try to merge different type of tools. So we inserted also CAM, which I will show you later. So as I was saying, the principal goal, the main goal was to use this type of sensors in order to take the orientation of the tools that are used by skillful technicians in different type of application like gluing, welding, for example. And then since we'll have, for example, the orientation and the position of the tool, will transfer almost seamlessly that position of the tool to a robot tool that will mimic that behavior of the tool that was used by the technician. So yes, the idea was to have very skillful technician that will use the tool, and then we'll transfer that knowledge of the technician to the robot. Okay. So in this slide, what you can see, it's the flow, I would say the workflow for the gluing process. So what we have done was to use this magnetic tracker, starting with him, and by having a technician simulating that it's putting glue on the window of a car. Then we merge it. So as I told you previously, we have some issues when we are taking the trajectories with the magnetic tracker. We had some deviation in relation um, to the position. The orientation was quite good. We didn't have that many problems using having the data from the orientation, but for the position, we have some deviations. So we thought, what tools do we have in the market that can help us do the trajectory quite seamlessly? Well, what is in terms of output of the skillful technician, the most important thing it's actually the orientation, because the position, if you think of different type of solution that exist, the position you can take it from CAM, and with quite with very high precision, right? Because CAM, it's a software that will help you to generate trajectories for anything you desire, and the precision is very precise. It's very accurate. So we said, okay, then if you have this position that is very accurate, why don't use, that was our main thought, why don't use directly come and then give it to the robot? And in that case, he will put the glue with no problems. But the thing was that this technician, the CAM could not do something that the technician were very experienced, and they knew how to avoid some mistakes when putting, for example, the glue. Um, and what we understood is that the technician were, when they were putting the glue, they were making uh, like dynamic variation of how they hold that tool. So our idea, okay, was for position, it's clear. We can have the position, but for the orientation, we cannot do that dynamically in the CAM software. It will be much more challenging to have for each point, for each target of the trajectory to make it exactly as that specialized technician will do. So with the magnet, we took those ideas, we take the cam, from the cam, we take the trajectories, and then from the magnetic tracker, we took the orientation of the tool. So since with both of this merge of data, we achieved uh, a very close deposition of glue as it was done by the technician. Okay. So, okay, taking this in consideration, we take the cam, we take the magnetic tracker, and we merge the data from both of them. And what we'll get in that file, let's see, this position, velocity, and orientation. And since we in PeneloPe are working with AutomationML. So we have a dedicated file where we store this type of data that is called PathML, but it's AutomationML based. In my previous training, I have spoke a lot about AutomationML and especially about the PathML, how we are working. But just as a recapitulation, this PathML file serves as a neutral data exchange file. So we store data inside this file regarding trajectories. So if we take this example, and it was built for the PeneloPe project, this structure, this type of file, the PathML file. So the idea of the PathML file is to have a neutral data file that can exchange data with multiple different tools. So as tools, I mean like offline robot programming simulator, so robot simulator software, or we could have simulation software, like multi-physics simulation software in terms to determine if, in this case, for the glue was deposited in the correct amount or not, if the trajectory influences the amount of glue that, or how the glue will spread along the window. So as a generic view for the PathML, what you should understand it to be is a neutral file that can be imported in multiple different tools, and the data content of that PathML file is data related to trajectories. So it gets trajectories from in this case, from magnetic tracker CAM software, and also have some process parameters inside. Later ahead, I will show you more about this, but it has process parameters. So if we are talking about gluing, uh, some process parameters could be the speed of the tool that is moving around to deposit the glue. Another one could be the glue deposition flow, and so on. We have multiple parameters that are important, for example, for different simulation softwares. And those different simulation software get this data directly from this neutral type of file, okay? So yes, this PathML file then is imported here, as you can see, into an OLP software, so offline robot programming software, um, that checks if the trajectory is done, it's correct, okay, just to check. And also, if necessary, it could be done some adjustments. But basically, is to check that if the trajectory was it's suitable. Then after doing the simulation here, in other process, we are doing uh, multiple type of simulation. This is just one that is a robot simulation, but we use also, as I was saying to you, like multi-physics simulation to see the spread of the glue, uh, all of this type, if the glue will have good adhesion or not, etc. So moving forward, what we have here is also after doing the simulation, we have the generation of the robot code, of course, and then the robot code is transferred to the real robot that can perform the actual gluing. Okay, so what we have here in summary is the transfer of knowledge from a skilled technician in terms of orientation. The CAM trajectory is more simple to get it. So we get it from a computer-aided manufacturing software. Then all of this data is transferred to a PathML. The PathML serves as the primary container of this type of data, and it shares it with the multiple softwares for simulation purposes. And then it can be, if the data is proved to be good, it's sent then to the real robot to perform actually the gluing. Okay. So here you can see some images of the magnetic tracker. The magnetic tracker, as you can see, is in this position right here. It's not exactly on the tip of the tool, but we are doing a transformation. So a transformation of these coordinates to match this type, or so it's a mathematical transformation, okay? Just for us to get the position of the tip of the tool, okay? So this is the sensor, and this is the base, okay? So this is the source. So all the trajectory are for us are given in relation to this source. Once the once the data is captured, usually we save it into a CSV file. So this CSV file, this file that you can see, it's the output from the magnetic tracker sensor. So what we have here, usually this column here, it's X, Y, Z, and we have here your pitch roll. Yes. So moving forward, as I was saying to you, after we have that uh, after we have collected the data from the magnetic tracker, but I was saying, okay, we have here X, Y, Z, but sometimes we have some errors. And for us to make sure that in fact the trajectory is 100% correct, we use a precise software for us to generate the trajectory of the cam. Okay, so we take the XYZ in fact from here, and then the yaw pitch roll, we take it from the magnetic tracker. Yes. After that, the output from this CAM software is a numerical control file where we have also X, Y, Z, and we have also orientation. But in this case, we ignore the orientation because it's not needed. And what we will do, we will merge this file with the previous file from the Liberty, from the Liberty tool. Okay? So from the magnetic tracker. And we use this built-in software that is able to merge those files. So we select here, for example, the mimic solution. In this case, we have here the position of the sensors in relation to the TCP. So usually we use like only these two distances, which are most important because they usually the sensor and the TCP are on the same plane. So what it means, we need only the Y distance and the Z distance to make to define where is the TCP and where is the sensor, and then we use some transformation equations to reposition this point here into the TCP. So when we transfer the data to the actual robot will know that its TCP should be here and not here where actually the sensor is giving the data, correct? Okay. Here we can add for the gluing process, we can add some process parameters like end effector velocity and the glue flow rate. Okay, and then we can generate the path.ml file. This path.ml file, as I told you, has the path data, so numerical control file from the CAM, and also it has included the orientations that like Euler angles that are coming from the magnetic tracker, as I was saying, and it has some process parameter data. This has as an output a path.ml file, as you can see it right here. This square right here, it's a screenshot of AutomationML editor. So in the AutomationML files can be opened in the AutomationML editor, and you can see it, see the KX structure. So KX is a tree type of structure where you can see what are the elements inside. So usually we have layers. If we will have multiple layers added, the different tracks, a track with a continuous deposition, a continuous movement of deposition of material. So we consider one track. For example, in this case, we have 2 points, but we can have more. In any case, the path.ml file, as I was saying, it can be opened as an editor, but it's an XML type. It's an XML based file. Okay, the AutomationML, it's an XML. It's based on XML. So the data, it's XML, it's ASCII, so the data can be it's human readable, and you can develop multiple software to retrieve whatever type of data that you need inside this path.ml file. This is an image of the magnetic tracker capturing the human motion that was captured and then transferred to the simulation software. Okay, this in the top images is a simulation software based on robot decay, and below is the equivalent movements when it was done to apply the glue. Okay, here we have a video just show you. Okay, so this is what we are doing to capture. We have this tool, the sensor is here, maybe not very much visible, but it's here. If you can see this gray point here, it's the sensor. And we are we are collecting the orientation used by the technician. Okay. Then the output file, as I told you, is a CSV file. And this CSV file uh, is then merged with the CAM software. So we have the CAM trajectory, which is this one, which was already obtained. And this one, the CSV file, is the file that captured the trajectory of the technician. After merging these files, we can add here the process parameters. The process parameters which were simulated usually, or we usually, sometimes we start with some predetermined values, saying, for example, for the end effector velocity, it's 60 millimeters per second, and the glue flow rate, it's a given value, okay? So all of this data then is simulated in the multi-physics simulation, and the data is retrieved from the PathML file, okay? So after generating the PathML file, this is the PathML file that we obtain with the different data for trajectories. Okay, let me put it here. We get the tracks with the different points. We can see here the XML view of this file, is both of them are the same. And yes, as a conclusion, this file can be used for as direct input for multiple engineering tools. As I was saying, the simulation in this case was done simulation of that glue by one of our partners in the PeneloPe project to see if the amount of glue was appropriate, etc., just to optimize a little bit the process. Then we have here a simulation of for the robot simulation, and of course, from the simulation we can have as an output the robot code and make them the application. Okay, moving forward. This was another application that we have tried. We've tried to make it with welding. So in this case, in the top row of images, what you have is a technician simulating that he is welding. In this case, we were not exactly welding; it's just a simulation, just to take the trajectories. So um, in the same way as we have done it for the gluing process, we have done it for the welding. We have connected here the sensor from the magnetic tracker, retrieving the orientations, and then those trajectories, those orientations were sent to the robot simulator. From the robot simulator, we generated the robot code, and then we have actually performed um, the welding. Okay. In summary of all of this process, we have usually a workflow for our PathML file, for how is the process, for example, for the gluing application. We usually start here with the CAD design of the different parts. You know, the CAD goes to CAM where we generate the trajectories. In this case, is a integrated. It's not pure CAM. We use the Liberty project, the magnetic tracker, in order to get to retrieve the skills of the technicians, and we merge it with CAM. And then that output is sent to the PathML. PathML serves as I was saying, as the neutral data file, and this data file then can be shared with the different simulation organizations. So the multi-physical simulation part, the robot simulation part, and then they actually check if that data is okay. If this PathML file, okay, the data that is in this PathML file, for example, results into a multi-phase simulation that is not optimal for the process, then we have this communicated to the CAD or to the CAM experts, CAM, and also, of course, in this case, the technician, to see if some changes can be done, and those changes are then performed, and then the PathML is updated. Then it's done again the multi-physics simulation or the robot simulation, in this case both, and then it goes um, to actually gluing of the part. Okay. Then we have also, of course, inspection quality control, uh, where they communicate also the data. In terms of readers, as I was saying, the flow usually goes from CAM. It generates the numerical control file. The numerical control file goes inside the PathML generator, so to generate the PathML file. So in this case, the numerical control file and also the file that comes from the magnetic tracker are input for this software, and then it generates this PathML file. And then after having this standard and machine independent file, this can be imported in multiple softwares from the different type of partners that we have in this project, for example. The only thing that they need to do is to make an PathML reader, which is quite straightforward because the PathML file is written, as I was saying, I said to you, in XML type of format. XML, it's follow the XML standards, so it's human readable, and you just need to retrieve the data and then use it for whatever type of application or whatever type of um, expertise that you are doing. If you are in the multi-physics simulation, you'll use it for multi-physics. If you are on the offline robot programming, you are using it for that, and so on. Okay. Uh, for me, this with this I end this presentation. Okay. If you will have any questions, just let us know. Write to us. You can write to me to this email, and I'll be happy to clarify more your questions. Thank you for listening.